All right, let's jump right into this explainer and crack open your computer's brain. We're going to uncover how your CPU actually processes instructions to make, well, literally everything work. Whether you're typing up an essay, gaming, or just mindlessly scrolling the web, the whole shebang boils down to a microscopic sequence of events happening deep inside your device. Today, we're building a complete study guide focused totally on the Fetch-Decode-Execute cycle. We'll break down the jargon, check out some real examples, and make absolutely sure you're ready to crush this topic on your exams. Here's our quick roadmap for today's study guide. 1. The core CPU cycle. 2. Anatomy of an instruction. 3. Step-by-step, the fetch. 4. A 5-cycle example. And 5. When programs branch. Let's get to it. Kicking things off with Section 1, the core CPU cycle, the true heartbeat of the computer. Now, this cycle is the fundamental mechanism of literally any computer, and it's happening billions of times a second. If you were to pop the lid off your desktop, you'd find two absolutely critical components: the main memory, which stores your programs, and the central processing unit, or CPU, which actually does the heavy lifting. The CPU processes data by constantly fetching instructions from that memory, decoding what the heck they mean, and then executing them. Like the slide says, it is quite literally the heartbeat of your machine. To really get this, think of the CPU like a highly efficient factory, and these registers, they're at your specialized workstations. First up, we've got the program counter, or PC. This one is vital because it holds the memory address of the very next instruction to be executed. Next, the memory address register, the MAR, holds the address that's about to be sent out to memory. Then, the memory data register, or MDR, catches the actual data when it comes bouncing back from memory. The current instruction register, the CIR, securely holds the instruction we just fetched so it can be decoded. And finally, the accumulator. This is a general-purpose register where all the mathematical and logical results are actually stored and worked on. Now, connecting this factory to the outside warehouse, your main memory, are the buses. You can think of the address bus like a delivery label, sending the location out to memory. The control bus is kind of like a traffic light, sending read or write signals. And the data bus? That's your actual delivery truck, hauling the content straight back to the CPU. Moving on to Section 2, Anatomy of an Instruction. Let's decode the code. For your exams, you absolutely have to nail this split. Every single instruction is made up of two distinct halves. On the left, we have the opcode. This tells the CPU exactly what operation to perform, like load or add. On the right is the operand. This tells the CPU what to actually apply that operation to. The operand might be a raw number, say the number 5, or it could be a memory address pointing to where the data is stashed. A really common pitfall in exams is mixing these two up. Just remember, opcode is the action, operand is the target. You know, you won't actually need to define how an opcode is structurally made up in the exam, but you will need to interpret them. So definitely use this table as a quick review guide. Let's highlight a couple of crucial ones. A load opcode tells the CPU to grab data from memory and pull it right into the accumulator. An add opcode tells it to add the contents of a memory address to whatever is already sitting in that accumulator. A store opcode is just the reverse of a load. It takes the result waiting in the accumulator and writes it back into main memory for safekeeping. We'll touch on the branch always opcode in a minute, but keep this list handy as we start looking at actual programs. All right, Section 3, Step-by-step, the fetch. Okay, let's walk through this sequence step by step. It's like watching our instruction travel from the distant land of main memory straight into the CPU. Step 1, the CPU checks the program counter and copies that exact address into the memory address register. Step 2, that address gets pushed out along the address bus over to main memory. Step 3, but memory doesn't know what to do with it yet, so the control unit flashes a read signal down the control bus. Step 4, now main memory knows what's up. It grabs the data stored at that address and sends it flying back down the data bus into the CPU's memory data register. And since we're fetching an instruction here, that data gets copied straight into the current instruction register. Step 5, and guys, this is a massive pitfall to avoid in your exams. Remember that the program counter increments before the instruction is executed, not after. It simply adds 1 to itself so it's locked and loaded, pointing at the very next instruction. Let's see this in action in Section 4, a 5-cycle example. Let's treat this next bit like a mock exam practice question. What does this specific 5-cycle program actually do? Feel free to pause the explainer right here for a quick self-assessment if you want to try it yourself before we walk through it together. Okay, let's solve it. In the first 2 cycles, we fetch, decode, and execute a load command, followed immediately by an add command, storing the final result of 3 plus 1 in the accumulator. Here's how. In cycle 1, the CPU decodes a load opcode. It heads to memory location 0101, finds the number 3, and pulls it straight into the accumulator. In cycle 2, the CPU fetches the very next instruction, which decodes into an add opcode. It goes to the target memory location, finds the number 1, and adds it to the 3 that's already chilling in the accumulator. So now the accumulator holds the number 4. Then the final 3 cycles take that result of 4, store it safely away in memory, output it for us to actually see, and then pull the plug on the program. Cycle 3 decodes a store command. It grabs that number 4 from the accumulator and pushes it back out into main memory. Cycle 4 decodes an output command. Even though the result was safely stored away in memory, a copy is still sitting in the accumulator, so it simply outputs that value to your screen. And finally, Cycle 5 decodes a halt opcode. The program officially brings itself to a full stop. And this perfectly shows how this simple, high-level code you write is actually translated into these microscopic, sequential fetch-decode-execute cycles. When you type something super simple like sum equals num1 plus num2, followed by print sum in a language like Python, you are actually triggering this exact 5-cycle dance. Just constant data moving back and forth between memory addresses and the accumulator. Moving to our final part, Section 5, when programs branch. Time for a plot twist. See, real programs use logic that totally disrupts that simple step-by-step sequential flow we just looked at. If you write an if statement, for example, if age is greater than 18, the program might need to skip certain lines of code entirely based on the answer. We call this branching. All right, here's a perfect practice question for your exam prep. How does the program counter update differently during a branch command compared to a standard sequential command? Well, in a sequential program, exactly like our 5-cycle math example, the program counter simply increments. Address 0 becomes 1, 1 becomes 2, 2 becomes 3. Easy. But in a branching program, the program counter is replaced entirely. The program effectively jumps to a totally different spot in memory. When the CPU executes a branch opcode, it doesn't just add 1, it overwrites the program counter, allowing the program to jump to a completely different neighborhood in memory. Let's say the current instruction is fetched and decoded, and the opcode is branch always. The operand attached to it might be memory address 1001. Instead of the program counter just quietly adding 1 to itself, the CPU grabs that operand, 1001, and completely overwrites whatever was in the program counter. So when the next fetch cycle kicks off, the CPU checks the program counter, sees 1001, and jumps completely out of sequence to fetch its next instruction from way over there. When you zoom out from all the individual registers and buses, the sheer scale of this operation is honestly mind-blowing. Every single mouse click, every key press, every single pixel update on your screen is the result of this tiny fetch-decode-execute loop, moving data from memory, calculating it in the accumulator, and storing it back. So as you're gearing up for your exams, keep that completely mind-blowing reality in the back of your head. You now know the full cast of characters, from the program counter all the way down to the data bus. You know the vital difference between an opcode and an operand, and you know exactly how a CPU can branch and jump around memory. Think about the device you're holding right now. How many billions of those exact cycles just happened while you were watching this explainer? Pretty wild, right? Thanks for hanging out with me. Rewatch this guide as much as you need, and seriously, good luck on those exams.